Welcome to another learning opportunity. Today, we shall have the extreme value theorem and optimization problem. This is your teacher, Jennifer Basilio de Leon, at your service. In today's discussion, we shall have the following goals. Illustrate the extreme value theorem through graphs, determine the minimum and maximum point of a function using either the first derivative test or the second derivative test. Maximize the available resources by applying the concept about extreme of functions, and solve optimization problems that yield polynomial functions through mathematical reasoning. All aboard! Let's start our discussion by defining what relative maximum value is. The function f has a relative maximum value at the number c if an open interval containing c exists on which f is defined, such that f of c is greater than or equal to f of x for all x's in the interval. Considering this graph, if we will trace this graph, we can see that the highest point can be found at this point or part of the graph. And with this, we can say that this point is the relative maximum point of the function on that particular interval. Now consider the function f of x equals negative x squared plus 2x plus 3. Now on its right, you can see its graph. Now let's say we're considering the open interval from negative 2 to positive 3. And on the graph, we can say that the maximum points or the highest points on the graph can be found at 1, 4. So on the open interval from negative 2 to positive 3, we can say that the relative maximum value of the function is at x equals 1, which is positive 4. We can say that this point is the relative maximum point of the function on the interval from negative 2 to positive 3. Consider the function f of x equals x raised to the fifth power minus 2x cubed plus x. Also, consider the open interval from 1.4 to positive 1.2. And on this interval, we can clearly see that there are two relative maximum points. This means that to be considered as the relative maximum point, that point may not be the highest point on the graph. As long as that point is higher than the points which are adjacent to it, then it is considered as the relative maximum point. For example, if we have a point on the left of negative 1, 0, we can see that negative 1, 0 is still higher than this point. Now let's get a point on its right. From here, we compare its height. We can say that negative 1, 0 is higher than this point on its right. Therefore, negative 1, 0 is a relative maximum point of the function, aside from 0.45, 0.29. In addition, we can say that at x equals negative 1, the relative maximum value of the function is 0, while at x equals 0.45, the relative maximum value of the function is 0.29. I hope you were able to grasp the concept of the relative maximum value of the function. With this, Let's move on as we discuss the relative minimum value of the function. The function f has a relative minimum value at the number c if an open interval containing c exists on which f is defined such that f of c is less than or equal to f of x for all x's in the interval. So for example, this is the open interval. We can say that at point A, we can find the relative minimum value of the function. And we can say that this point is the relative minimum point of the graph. Consider the function f of x equals 2x squared minus 4x plus 1. Now we can see the graph on its right and also consider the open interval from 0 to positive 2. On this interval, we can clearly see that the lowest point is at 1, negative 1. So we can conclude that at x equals 1, we can find the relative minimum value of the function, which is negative 1. And we can consider this point as the relative minimum point of the graph. Now let's have another example. Now consider again the function f of x equals x to the fifth power minus 2x cubed plus x. Also consider the open interval from negative 1.2 to positive 1.2. Now we can see on this portion of the graph, there are two relative minimum points. These two are considered as the relative minimum points of the graph. So this means that the relative minimum point may not be the lowest point on the graph. As long as this point is lower than the points adjacent to it, it can be considered as the relative minimum points. For example, the point with coordinates 1, 0 is not the lowest point on the graph. However, this is lower than the point from its right and from the point from its left. So we can also say that this is a relative minimum point on the graph. Furthermore, we can say that at x equals negative 0.45, the relative minimum value of the function is negative 0.29, and at x equals 1, the relative minimum value of the function is 0. I hope you were able to get the concept of the relative minimum points and the relative minimum value of the function. Let's define the relative extremum. If f of x exists for all values of x in the open interval from a to b, and if f has a relative extremum at c, where c is greater than a but less than b, and if f prime of c exists, then f prime of c is equal to 0. This definition implies that we can equate the first derivative of the function in order to find the critical value in the function. Now consider f of x equals 2x squared minus 4x plus 1. Let's find the first derivative of the function. So we will have 4x minus 4. And then in order to find the critical value, we can equate f prime of x to 0 in order to solve for the critical value. We transpose negative 4 to the left to isolate x. And then we can divide both sides by 4, so x is equal to 1. Therefore, we can say that the critical value in the function is x equals 1. Fill in the table. So f prime, the first derivative is f prime of x is equal to 4x minus 4. Its critical value is x is equal to 1. Now, to get the critical points, we have to evaluate f of x. We have to evaluate f of x at x equals. Let's evaluate f of x at x equals 1. So we will have 2 times the square of 1 minus 4 times 1 plus 1. Simplifying this, we will have negative 1. So therefore, the critical point is 1, negative 1. The question is this point a relative minimum point or the relative maximum point? Now, using or looking at the graph, we would be able to see whether it's a relative minimum or a relative maximum point. Now, let's locate 1, negative 1. Okay, here is 1, negative 1. And then, since it's the lowest point within the interval, then we can say that it's the relative minimum. Now we're ready to discuss the extreme value theorem, which is described as if the function f of x is continuous on the closed interval from a to b, then it has an absolute maximum value and an absolute minimum value, the closed interval from a to b. Consider the given. F of x is equal to 2x squared minus 4x plus 1 on the closed interval from 0 to 3. Now, based from this theorem, we can find an absolute maximum and the absolute minimum value on the interval 0 to 3. Now, let's start by finding the first derivative in order to find the critical value or values of the function. Now, getting the first derivative, we will have f prime of x is equal to 4x minus 4. Now, we equate this to 0, just like what we did a while ago. We will have to divide both sides by 4, so we have x equals 1. Okay? Now, let's complete the table. F prime of x is equal to 4x minus 4. So then our critical value is x equals 1. Now, since we are dealing with a closed interval, the endpoints of the interval are also the critical values in the function. So we will include x equals 0 and x equals 3. Now, to get the coordinates of the critical points, we have to evaluate the original function at these 3 critical values. So let's start first with f of 1. So 2 times the square of 1 minus 4 times 1 plus 1. We simplify that. We will have negative 1. So the critical point is 1, negative 1. What about when x is equal to 0? Okay, so we will have 2 times the square of 0 minus 4 times 0 plus 1. Simplifying that, that will give you 1. So our critical point would be 0, 1. Now, when x equals 3, let's evaluate when x equals 3. So we will have 2 times the square of 3 minus 4 times 3 plus 1. So this will be 9. Then we can have this as 12. Then we have 18 minus 12 plus 1. Simplifying further, we will have 7. So the critical point would be 3, 7. And then we are ready to determine whether it's a relative minimum, maximum, or an absolute maximum or minimum value. Now we are ready to determine the extrema of the function. The first critical point is 1, negative 1. On the graph, we can see that it is the lowest point on the graph. So we can say that it's the absolute minimum point of the function. Hence we say that at x equals 1, we can get the lowest value of the function, which is negative 1. The next critical point is 0, 1. On the graph, we can say that this is the endpoint of the graph. Now to determine whether it's a relative maximum, minimum, or an absolute minimum or maximum, we compare this point to all the other points in the graph. 0, 1 is neither the lowest or the highest point. And just choose between relative minimum or relative maximum. However, we compare the points which are immediately to its right and left. So we compare the points immediately to its right. The points are lower than the points 0, 1. However, there are no points immediately to its left. So we have nothing to compare. Therefore, we say that this point is neither a maximum or a minimum point. Now let's proceed to the third critical point, which is 3, 7. This is the endpoint of the graph, and we compare 3, 7 to all the other points in the graph. We can see that this point is the highest point in the graph. So we say that this is the absolute maximum point. Hence, we say that at x equals 3, we can get the absolute maximum value, which is 7. Now consider the example f of x equals 2x cubed minus 4x squared minus 1 on the closed interval from negative 1 to 2.5. The first derivative of the function, so we will have 6x squared minus 8x. And then in order to find the critical values in the graph or in the function, we equate first derivative to 0. Now let's factor this. We will have the greatest common factor, which is 2x, and then this will be 3x minus 4. And then using the 0 property, we can equate each factor to 0, since when you multiply these two, the result is 0. So in 2x equals 0, we will have x equals 0. In 3x minus 4 equals 0, we would be able to get, okay, we transpose negative 4 to the right side, we have positive 4, and then divide both sides by 3, so we will have x equals 4/3. So we fill in the needed data in the table. So the first derivative of the function is 6x squared minus 8x, and then the critical value or values is x equals 0 and then 4/3. Now, since we have the function, we are considering the function and the closed interval from negative 1 to 2.5, We consider the endpoints as critical values also. So we have x equals -1 and then x equals to 2.5. Now we determine the critical points by evaluating this function, the original function, at x equals 0, x equals 4/3, x equals -1, and x equals 2.5. So for 0, we will have 2 times 0 raised to the third power, 4 times 0 raised to the second power minus 1. Then we have -1. So the critical point is 0, -1. Now for 4/3, we will have, okay, f of 4/3. So 2 times 4/3 raised to the third power minus 4 times 4 over 3 raised to the second minus 1. And then the cube of 4 is 64. And then cube of 3 is 27. Then we have the square of 4 is 16. And then the square of 3 is 9. Okay. And then we simplify using our scientific calculator. We will have, okay, -3 and 10 over 27. So the critical point is 4/3, -3, and 10 over 27. We will have 2 times -1 minus 4 times +1 minus 1. So simplifying, we will have -2 minus 4 minus 1. Simplifying that, we will have -7. So the critical point would be -1, -7. Now, what if we have x equals 2.5? Okay, using our scientific calculator, we will have 5.25. So the critical point is 2.5, 5.25. Okay, we were able to determine the critical values and the critical points by using the first derivative of the given function. Now, it's time to determine whether it's a relative or absolute, maximum, or minimum. So let's move on. Using the graph, we can say that, okay, since we have 0, -1, here is 0, -1. This point is higher than the points on its right and on its left, so we will have a relative maximum. Now, if we have 4/3, -3, 10 over 27, okay, since this is lower than the points from its right or from its left, then we can say that it is a relative minimum. And then we have the endpoints. At -1, -7, we can see that this point is the lowest point on the graph, so we can say that this is the absolute minimum. And on the other hand, 2.5, 5.25 is the highest point, so we can say that this is the absolute maximum. Are there questions? If there are, kindly type in the comment section, and once I have read the comment, then I'll respond to your questions. Now, at this point, I have a question. How do we know whether a critical point is a relative minimum or a maximum point without using graphs? Now consider the function f of x equals 2x squared minus 4x plus 1. A while ago, we were able to get already the critical value and the critical points on this graph. And this time, let's determine whether it's a relative minimum or a maximum without the use of its graph. Now, there are two ways in determining whether it's a relative minimum or maximum. The first method is using the first derivative test. Okay? The first method is using the first derivative test. There are three conditions. The first condition is if the f prime of x for all x immediately to the left of critical value c are positive and the f prime of x for all x immediately to its right are negative, then the point is a relative maximum. So literally we will get a positive number and then on the right we have a negative number. The second condition is that if the f prime of x for all x immediately to the left of critical value c are negative, and the f prime for all x immediately f prime of x for all x immediately to its right are positive, then the point is a relative minimum. So after evaluating, we would be able to get a negative value using a point on the left of the critical value, and then if we will get a number at the right of the critical value, then the result would be a positive number. However, if the result after substituting a value on the first derivative of the function, the result would be the same sign, then it's neither a relative minimum nor a relative maximum. So let's try. We were able to get already the first derivative of the function, which is f prime of x equals 4x minus 4. And then we get a number. Take note, the critical value is x equals 1. We get a number coming from its left, so probably we can consider x equals 0. Now, if we will evaluate f prime of x at x equals 0, we will get negative 4. So we have a negative number. Now, considering a number on its right, let's say we have x equals 2. Okay, now let's evaluate f prime of x at x equals 2. Then we will have 4 times 2 minus 4. So we will have 8 minus 4. Then we will have positive 4. Then we will have this right side, we have positive. Now, since we have negative positive, we shall use the second rule. That means that the point is a relative minimum. That is by using the first derivative test. Now this time, let's have the second method, which is the second derivative test. It says that if the f double prime of x is greater than 0, then the function has a relative minimum value at x equals c. Whereas if the f double prime of x is less than 0, then the function has a relative maximum at x equals c. Okay, so let's start working on. The function is f of x is equal to 2x squared minus 4x plus 1. The first derivative of the function is 4x minus 4. Now we get the derivative of the first derivative in order to get the second derivative. Then we will have 4. Now since 4 is greater than 0, okay, we shall use the first rule. Hence, we can say that at x equals 1, we will have a relative minimum. Now let's check on this example. We are asked to determine the extremum of the function defined by f of x equals 2x cubed minus 4x squared minus 1 on the closed interval negative 1, 2.5. Now let's use the second derivative test. Okay, we have now the first derivative, so let's get the second derivative of the given function. Therefore, we will have 12x minus 8. Now, we have x equals 0. Okay. Evaluating f double prime at x equals 0, then we will have 12 times 0 minus 8. So therefore, we have negative 8. Now, since it's less than 0, then we can say that this is a relative maximum. Evaluating f double prime of x at x equals 4/3, we will have 12 times 4/3 minus 8. Okay, then we can cancel 12 and 3, so this will be 4. Okay, and this is 1. 4 times 4 is 16 minus 8. Therefore, we will have 8. Now, since 8 is greater than 0, then at x equals 4/3, we will have a relative minimum. Okay, and then since we have x equals negative 1 and x equals 2.5 as a value on its endpoint, then we can just determine whether it's an absolute minimum or a maximum point. Now consider the function f of x equals x cubed. We get the first derivative of the function, so we will have 3x squared. So you will have 3x squared. Now, in order to find the critical value, we need to equate the first derivative to 0. Hence, we can have x equals 0. That's the critical value. Now, to get the critical points, we have to evaluate the original function at x equals 0. So we will have 0 cubed. Simplifying that, we will have 0. Therefore, the critical point is 0, 0. Now, in order to determine whether this value is a relative minimum or maximum, we can use either the first derivative test or the second derivative test. This time, let's use the second derivative test. Let's get the second derivative. We will have 6x. Now, evaluating the second derivative at x equals 0, we will have 6 times 0, which when simplified will have 0. Now, since 0 is equal to 0, it's not greater than nor less than itself. Therefore, we can say that it's neither a relative minimum nor a maximum. So, since we have arrived at 0. Now, let's verify using the graph. So, looking at the graph, this is 0. Now, here's the point 0, 0. We get a point on its left and check whether it's higher or lower than the point. Now, looking at it, we can say that 0, 0 is higher than the points on its left. Now, getting a point on its right, is it still higher than the point on its right? Now, looking at the graph, 0, 0 is lower than those points on its left. So, since it's not consistent, then we can conclude that the point or that the value is neither relative maximum nor minimum. The concepts we have just learned can be applied when optimizing our scarce resources. Now let me present to you the steps in solving optimization problems. First, you have to illustrate the given data in the problem. The second is to determine the optimization equation and the constraints. Next, we solve one variable in terms of the other variable using the constraint. And then we substitute the value of that variable in step 3 to the optimization equation. And then find the first derivative of the equation in step 4. Then set the first derivative of the function to 0 and solve for the critical value. And then determine whether the critical value is a relative minimum or a maximum using either the first derivative test or the second derivative test. And lastly, answer the main question in the problem. Now let's have a concrete example. You are asked to fence a rectangular lot and maximize the area for a vegetable garden. You're given 200 meters of fencing materials. What could be the dimensions of the vegetable garden? The first step is to illustrate the given data. Since we are given a rectangular lot, then we have to draw a rectangle and then identify its parts using variables. We have labeled the length and the width as x and y respectively. The second step is to determine the optimization equation and the constraints. Now, since we are asked to maximize the area, our optimization equation would be the equation for the area, which is A equals xy. Now, since you're given 200 meters only for fencing, that represents our constraints. Remember that fencing is an activity that calls for the concept of perimeter. So using the rectangle, the perimeter would be 2x plus 2y. And then take note that this 200 meters, okay, is equal to the perimeter of the rectangular lot. Okay, so our optimization equation is A equals xy, and then our constraint is 200 equals 2x plus 2y. Now we're ready to do the third step, which is to solve one variable in terms of the other variable using the constraint. So we have, now using the constraint, we will have 200 equals 2x plus 2y. Then we solve for y in terms of x, so we will have 200 minus 2x equals 2y. And then we divide by 2, therefore we will have y equals 100 minus x. So we were able to solve for y in terms of x. Remember that because we will need that later. Okay, and then continuing, we are ready to do the fourth step, which is to substitute the value of that variable in step 3 to the optimization equation. The optimization equation is area equals xy. Substituting, we will have x times the quantity 100 minus x. Simplifying, we will have 100x minus x squared. Then let's do the fifth step. We are going to get the first derivative. So we will have 100 minus 2x. And then doing the sixth step, we equate the first derivative of the function to 0 in order to solve for x. So we transpose 100 to the other side. We will get negative 100 equals negative 2x. And then we divide both sides by negative 2. So we will have x equals 50. Now let's see whether this critical value is a relative minimum or maximum. Let's use the second derivative test. Now, if we will have to get a double prime, okay, a double prime of x, we will have 100 minus 2x, that would be negative 2. Now, since a double prime of x is less than 0, then we can say that this is a relative maximum. So we are ready to answer the main question, which so we are ready to answer the main question in the problem, which is the dimensions of the vegetable garden. Since x equals 50, using this equation, we would be able to solve for y. So we will have 100 minus 50. We will have y equals 50. So therefore, the dimensions of the vegetable garden is 50 meters by 50 meters. To check on that, we can have a pair of numbers with which when added will give you 100. So like 50 plus 50, that's 100. So 50 times 50, that is 2,500. Now if you get another pair, if let's say if x equals 40, then y will be 60. If we get the area of that, that would be, or the area of the given rectangle when x is 40 and y equals 60, that would be 2,400. Again, whereas if we will have 50 for x and y, the area would be 2,500. Still, this is the highest product or the highest area. So that confirms our answer that in order to maximize the area of the vegetable garden given only 200 meters of fencing materials, we should have 50 meters by 50 meters. I hope you were able to get that and be able to solve other optimization problems. So if you have further questions on illustrating the extreme value theorem through graphs, determining the minimum and maximum point of a function using either the first derivative test or the second derivative test, maximizing available resources by applying the concept about extreme of functions, and then solving optimization problems that yield polynomial functions, you can just type in the comment section and then I will respond to your questions. Thank you for joining me in my class today.